Here in 5.2, we're going to introduce inner product spaces. Inner product spaces. And in the previous section, in 5.1, when we talked about dot products, we talked about things such as length of a vector, distance, angle between vectors, and all of those things could be calculated. We looked at the vector space R2, which is all two-dimensional vectors. We did some for R3, and then we generalized it for Rn for any dimensional vector space. But this is for what we normally think of as vectors. But remember, vector spaces can have all different types of forms. Some vector spaces can contain matrices. Some vector spaces can contain polynomials. So one inner vector space or inner product space that we've looked at is the dot product. And the dot product is an inner product space that's specific to Rn, and it's often referred to as the Euclidean inner product. And remember that the way we take a dot product, if we have two three-dimensional vectors, we multiply corresponding components together, and we add those up. So we call this U1, U2, U3, V1, V2, V3. It's U1, V1 plus U2, V2 plus U3, V3. So that's our dot product or our Euclidean inner product. But that can be generalized for matrices, polynomials, etc., as long as they meet certain criteria. So the definition of an inner product is, let's suppose we have vectors u, v, and w that are part of some vector space V. So V is our vector space, u, v, and w are vectors inside that vector space, and C is any scalar. So the inner product space, like a dot product, associates a real number. Remember, when we took the dot product, we got some number, not another vector or another matrix. We got a number. So it associates a number with u, v, or w, or whatever, as long as it meets the following four criteria. So that uv equals vu. So in our example of dot products, if we have u dot v and v dot u, those are equivalent. If we look at a simple example, 1, 2, divided onto 3, 4, that's 1 times 3 plus 2 times 4. Well, if we change the order of that, that doesn't change our answer. We take 3 times 1 plus 4 times 2, we still get the same answer. So if you swap the order of your operation, you still get the same answer. If you add a vector to one of them, then basically the distributive property applies. You take the inner product of u with the first one, the inner product of u with the second one. We could illustrate that being true with two vectors. If this is one vector, v is this vector, and let's do 3, 3 for w. V plus w would be 5, 5. And if we dotted u onto v plus w, we would get 2 times 5 plus 1 times 5. So we would get 15. Where if we did, I get that to erase, if we did u dot v, so 2 times 2, 2 times 1, and then u dot w, 2 times 3, 1 times 3, what's that, 6, 12, 15, same thing we got here. So we got 6 and 9, which is 15. So basically the distributive property works there. The third property, if we have a scalar that's multiplied times our inner product, that must be equivalent to multiplying that scalar times one of our vectors and then doing our inner product. So for example, if we have vectors 2, 1 and 1, 3, and let's say a scalar of 5, if we dot u and v together first, we have 2 times 1 plus 1 times 3, and then we take that answer times 5. Is that 5 times 5, so that's 25. Let's see, if we take our scalar times u, so if we multiply our scalar times u, we get 10, 5. And if we dot that with v, we have 1 times 10, 3 times 5, which also makes 25. So our third property holds for the dot product. And then if we take a vector and compute the inner product with itself, we'll get a positive number, something that's greater than or equal to 0, and it will equal 0 only if, in fact, if and only if the vector v equals 0. So for example, if you take a vector, dot it with itself, the only way you'll get 0 is if both of those are the 0 vector. Otherwise, you'll get a positive number. For example, if I have 1, negative 3, and I dot it with itself, positive times positive is positive, negative times negative is positive, and we get a positive answer. So that's an inner product space. So yeah, the dot product is an example, prime example of an inner product space, but it's not the only one. So let's go on, let's look at some other inner product spaces. All right, so let's look at an example, and let's do some calculations. Let's suppose that u is negative 4, 3, v is 0, 5, and that our inner product space is defined as 3 times u1 times v1 plus u2 times v2. Now notice this differs from the dot product. If you let that 3 off, you'd be multiplying the corresponding components, the u1 and the v1, u2 and v2 and just adding them together. This says let's have 3 times that first product and then just 1 times the second product. So this is where we define our inner product space. So we want to find a few things. We want to find the length of u, or that's called the norm. The norm of u. Take that off. And remember, just in standard vectors, sometimes you would see it written like that. This book uses a double bar on each side to represent the length. And the way we get the length is for a standard inner product, we square the first component, square the second component, add them together, take the square root. Here, since it could be in any inner product, not just a regular dot product, we do the inner product of u with itself, and then we take the square root of that. So for a regular dot product, not this inner product, but for a regular dot product, imagine finding the magnitude of this. You do -4 times itself, which is the first components times each other, plus the second components multiplied times each other, which that's basically the Pythagorean theorem. And then to get the length, take the square root of it. But since there are different inner products, we generalize that to saying, well, that's just the dot product of u with itself, and then take the square root of it. So in the case that this is our inner product, we do 3 times u1 times u1 plus u2 times u2. So that's 1648 plus 9, so 57. And then we take the square root of that. So this in here, this is the inner product u with u. And then we take the square root of it. If we want the norm of v, we take v with itself and take the square root. So if we let both of these be v's, it's 3 times v1 times v1 plus v2 times v2. So that's 0, so the square root of 25, or 5. So that's the norm of v. So the norm of u, square root of 57, the norm of v, 5. Now if we want the distance of those, this represents the distance, and the way we calculate that is we take the difference between u and v, and then we calculate the norm of that. So first of all, let's do u minus v. U minus v is -4 minus 0, 3 minus 5. And then if we want the norm of that, that's the square root of doing the inner product with this on itself. So I do 3 times -4 times -4 plus -2 times -2. So 16, 48, negative 2, so 4. So the square root of 52. Which, let's see, that simplifies a little bit. We can leave it as it is for now, though. So those are, what, 4 calculations that we've done. I don't guess we did this. We found the norm of u, the norm of v. We didn't calculate the inner product of u with v. The inner product of u with v would be 3 times negative 4 times 0 plus 3 times 5. 3 times the product of the first elements plus the product of the second elements. So that's 0, so 15. Now, if we wanted the angle between those two vectors, so let's see, our vectors u and v were negative 4, 3, 0, 5. Recall that using the dot product, the way we calculated the angle was that cosine of the angle between two vectors was u dot v over the magnitude of u times the magnitude of v, or the dot product divided by the norm of u times the norm of v. Well, the same thing applies whether it's a dot product or whatever. On the inner product, on an inner product space, so we take the inner product of u and v divided by the norm of u times the norm of v. So cosine theta for this inner product is 15. 15 is our inner product divided by the magnitude of u, square root of 57, times the square root of 25, which was 5. 5 and 15 reduce. So cosine theta is 3 over root 57. So if we take 3 divided by square root of 57, and then do inverse cosine, that's our answer in terms of radians, or in terms of degrees. 3 divided by square root of 57, inverse cosine, like 66.6 degrees. So that's the angle between those. So you may recall orthogonal. Orthogonal is just a fancy word for perpendicular. So in R2, using the normal Euclidean inner product, two vectors are orthogonal perpendicular if there's a 90-degree angle between them. So for example, if we look at the vector 5, let's not use that notation, 5, 0, and 0, 4, this goes to the right 5, up none. This goes left and right 9, up 4. Notice those are perpendicular to each other. Notice that cosine theta, remember, is our inner product over the product of the norms. If that's 0, if the inner product is 0, then it turns out that they are orthogonal. So we don't have to do the whole thing. If we find out that the inner product is 0, they're orthogonal. So for this example, if we take the inner product of u and v, and we'll use the standard Euclidean inner product, also known as a dot product, then 5 times 0 plus 0 times 4, 0 plus 0 is 0. So since that is 0, then yes, those are orthogonal. Now, in different spaces, different inner product spaces, it might not be what we necessarily traditionally think as being perpendicular, but that's just the way we define orthogonal. It's when their inner product equals 0. Now, real quickly, let's look at another inner product space. Let's see. If we have two polynomials, p and q, let's let it be a sub 0 plus b sub 0, or times b plus 0 plus a1 times b1 plus a2 times b2. So let's say that p of x is 1 minus x minus 3x squared. Q of x is x minus x squared. So this would be a sub 0, a sub 1, a sub 2. Here, b sub 0 would be 0 because there's not a constant. This would be b sub 1, b sub 2. So if we want the inner product space, the inner product here, we would have 1 times 0 plus negative 1 times 1 plus negative 3 times negative 1. So 0 minus 1 plus 3, or 2. If we wanted the norm of p, it would be the square root of the inner product of p with p. So 1 times 1 plus negative 1 times negative 1 plus negative 3 times negative 3. And then the square root of that. So the square root of 1 plus 1 plus 9, or the square root of 11. Let's see. If we want the distance between p and q, remember that's the norm of p minus q, which it turns out is the same as the norm of q minus p. So if we do p minus q, it's 1 minus nothing. Negative x minus 1x, so minus 2x, minus 3x squared minus a negative, so plus x squared, so that's minus 2x squared. Then if we want the norm, that's the square root of the first one times the first one, plus the second one times the second one, plus the third one times the third one, or the square root of 9, also known as 3. We could do this with matrices, with polynomials, whatever, as long as we begin by defining what our inner product is. Now, real quickly, let me just give you some definitions. Things that are always true for inner product space. One of them is called the Cauchy-Schwarz inequality. Must be R there. Inequality. And for two vectors, u and v, that are in the vector space big V, the absolute value of the inner product will always be less than or equal the product of their norms. So if you take the norm of U, the norm of V, and multiply them together, that will always be bigger than or equal to just multiplying U and V together to begin with, using the inner product. The triangle inequality, you may or may not have dealt with it before. U plus V is always less than or equal to U plus V. Basically saying if you add two vectors together, that's always, the resultant is always smaller than or equal to the length of the separate vectors combined. If I take a vector, add another vector to it, the resultant is that part. So U, V, U plus V. Notice it's a shorter distance to go U plus V, to take the resultant, than it is to take the distance U and the distance V and add those together. Sometimes that's the same, but this will never be larger than those two added together. Notice if U and V were in a straight line, then if I took the length of U plus the length of V, that would be the same as the length of U plus V. But otherwise, if they're not in a straight line, then this length plus that length, that will always be more, if they're not in a straight line, than the resultant. And the other one is the Pythagorean theorem. U and V are orthogonal if and only if the norm of U squared plus the norm of V squared is equal to the norm of U plus V squared. So thinking about two vectors, if we take the length of one vector squared plus the length of another vector squared, and that's exactly the length of the resultant squared, then those are perpendicular. Otherwise, they're not perpendicular. So hopefully we all know by this point that the Pythagorean theorem only applies to things that are perpendicular or orthogonal. So that kind of generalizes 5.2. One other thing that we may need, maybe one or two other things real quickly. If we want a projection, the orthogonal projection of U onto V is the inner product of U with V over the inner product of V with V times vector V. So the inner product of them together divided by the inner product of V with itself, which that's basically the norm squared, and then times the vector V. So this part gives you a scalar that basically takes the distance, if we think of this being U and this being V, it takes this distance, taking this, making a shadow onto V perpendicular to the path. So the length of this is given by that part. Let's see, no, the length of that is given by this part. This normalizes V. So I guess we could write it that times V over VV. This takes vector V and gets basically the unit vector in terms of V. And then, I believe that's correct. And then this takes that and gives it this particular length. So that takes U, projects it onto V. So the resulting vector is this blue part right here. So that's 5.2 in a nutshell.